What we said before is how you can synchronize the different events related to branching, for instance. You have rhythmic growth, and then you can create lateral branches, and how you can introduce delays and these type of things. So this is true for the branching system. You can synchronize everything smoothly via the different techniques that we saw. But if you want to synchronize the growth of different organs in different parts of the plant, you need to have a sort of strategy in order to do this. And I'm going to explain one way of viewing this problem that we designed during the ROMI project, during the European project, in order to create this type of simulations, where you have a growing plant, which is an Arabidopsis like plant that creates the leaves, and you see that all the events here that occurs, the sepals that are, and the flowers that are, the petals that are falling, the opening of the flower, the growth of the carpel in the center of the flower, all this needs to be synchronized in some way in order to reflect what occurs in the real world. Okay, so the question is how you would do this. So each organ on a plant has a developmental sequence, and you see the two cotyledons here, and then the leaf that can be. These are the elements of the leaf at different ranks of the main stem on the plant. But you could also imagine that you have similar sequence in time for the development of the leaf. Okay, so you have usually one organ when developing. It starts small, gets bigger and bigger and bigger, and then in the end stops the growth, and and this is controlled with a sigmoidal function, as we said last time. So in order to capture this, we also saw that it is possible to create a model and then to interpolate the model throughout time, and then to manipulate this model with a parameter tau that makes it possible to control the moment of the growth where you are. Okay, so to make different shapes, I remind you that we introduce different nerves of the petal, and these nerves are given different shapes, and then there is a possibility to interpolate in time between these different nerves, and this gives this possibility to have a petal at any moment in time. Okay? Okay, so we have this type of thing. Usually the time is here, I call it tau subpetal, so tau associated with petal, goes from 0 to 1. So it's not real time. It's 0, 1. So it's a completely arbitrary time. And I decided that 1 would be the mature petal, and that at time 0.70, there is this shape that is exactly in this configuration. Now I would like to do this for many organs and to have similar models for many organs, and then I would end up with a time which here would be tau subcarpel, that would correspond to a model of carpel development with an abstract developmental age between 0 and 1. Okay? And again, 0.5 would correspond, by my choice, to this moment of the development of the carpel. Okay? I am defining what does this abstract tau temporal value would signify in terms of development. 0.5 would be this one. Okay? Question, or it's okay?
Maybe working like that gives you lots of flexibility, but then you need for each module to define the synchronization with your global occurrence.
Precisely. So this is
Sorry.
what. No, that's okay. That's okay. You're right. But all these elements, they will be independent of each other. However, in the plant, they are part of a bigger system. And if we take the example of the flower is made of a pedicel, of a sepal, so sepal whorl, petal whorl, stamen whorl, and a carpel. And then each of the whorl is composed of a certain number of petals, sepals, etc. Okay? So and all this is developing together during the development of the plant. So the question, and now I assume that I have a specific model for the petal, for the sepal, a specific model for the petal, with a control tau that is between 0 and 1. So how can I gather all this in a sort of sensible manner in order to produce a model of the flower growth? Actually, the flower itself could be understood as one organ where there would be a tau flower, and I could exactly play the same stuff, saying that 0 is the birth, carpel that is almost about to be pruned out from the plant is the last moment of the carpel's life, and then there are stages of the flower development that can be even studied in a botanical manner. I mean, you could say that the emergence of the sepal would correspond to stage 2. The fact that the petals are folding, are bending backward, they would correspond to stage 3. The fact that the carpel starts to be visible could correspond to stage 4, and so on. So what I would like ideally to do is to make in correspondence this model of the development of the flower with this model of the development of a petal for each petal and potentially for each flower. So what I'm going to do is to distort the temporal view of the flower in order to map it to the temporal view of the petal. So I call this a timeline warping, because this is the timeline of the development of the flower, and this is the timeline of the development of the petal. And then to adjust the two, I need to say this at this point. So it's not a realistic one here, but at this point, for instance, of the development of the flower, this is this petal that you will find. Okay, this function can be linear, but it would be very surprising that it is linear. In general, this is not non-linear. This is why this is called warping function, because I try to stretch this time so that it matches the other time, but in potentially non-linear manner. Okay? To represent this stretching, you need ways. So usually we use functions, and one of the very common functions that can be used is the heal function. I reused it from yesterday because we have seen this. And if I put in abscissa the developmental time of the flower, I will say that the petal will develop according to this function. So in the beginning, basically, it will be very small, and then the petal will open rapidly, and then will saturate, will reach a final size quite rapidly before it is pruned out from the plant. This you can do for the whole elements of the flower. So if you have the time line of the flower, you could align on this timeline the pedicel, the sepal, the petal, the stamen, and the carpel. And the petal whorl, so the whorl itself, how it opens. And then in the whorl, you could also see each petal, how it should develop, and how the petal whorl tau should align on the petal tau. So sorry, the petal whorl tau should align on the petal tau. Okay, so you have a sort of hierarchy of timeline alignment functions, and if you give this hierarchy, then you synchronize everything in your system. So you need to design this by hand. You need to study the botany of your system, and see where and decide. For instance, when the flower is developing, petal will open at this point, petal will be mature at this point, petal will fall at this other point, and then give and then through a heel function or through other things, give a function that maps one timeline onto the other one. It's clear? I see that you are thinking. Nabil?
Is it important that it's a heel function? Because
no, heel function is just for the example.
Okay.
Because it
linear, piecewise linear.
Piecewise linear would do, or any function, even decreasing function. You could have for some reasons things that are decreasing, and then you could have decreasing function. In plants, most of the time this would be increasing function of time, but
yeah, and you would expect monotonic.
Monotonic, yes, most of the time. But we could imagine we could imagine. I don't have any example, but there could be. I could imagine that. Let me see. Well, most of the time it would be monotonic in plants, yes. So either, and monotonic and increasing. Okay. Now that we have aligned every organ on the timeline of the flower. So now, if I have a time, because this timeline of the flower is still between 0 and 1, and what I want to do is to put this in real time. But actually, it's exactly the same procedure. I take the real time between t0 and t final, and what I need to do is to align this real time with the 0 and 1 of the flower. And in this way, I will synchronize everything, the petal, the sepal, etc., on the flower, and the flower on the real time. Okay? So this is what I called this hierarchical timeline warping. Okay? Because it's just a way to synchronize everybody in a hierarchy of mapping. Okay, and thanks to this, you can describe rather precisely the development of a flower. So I propose that you try this example 1, and that we look at this example to really understand how it works, because it will be one of the key points in making a realistic model, to have this right synchronization between the objects.
One question, because you can have many levels, including levels of details or modules that evolve at very different speeds or have longer fates or not, does that suggest you would be interesting to have also varying time steps in the overall simulation?
It could be that you have varying,
so if you have a tree, it grows it goes faster because you are growing branches, and then when it goes flowering, you basically need shorter time steps. I don't know.
Yes, it could be. Then we would need to, yes, you could have time step. Well, usually when you have a simulation, since you want to see the simulation from the outside, you assume a unique time step at which you will look at all the phenomena. But you could imagine that you want to model more precisely the development of the flower, and then it could be local to your simulation, you change the time step, or it could be another simulation where you have a different time step. It's rare, I think, that you find different time steps in a simulation. It's not impossible, but it's not the most common. Okay? So have you tried to figure out what is in this example 1 of this part 4.3? So this is the animation. Can you all see this? The carpel is growing, and then the petal and the sepal are falling out. I didn't model the stamens here. So have you looked at the code, and are you able to see the main big parts of the code and how it works? So I leave you some minutes to look at this, and then we can discuss this together. Okay. There is a notion of petal model, for instance. If I use petal as a module, I would need to put in the petal many of what characterizes a petal would be its length, would be its width, would be its shape. It's a bit vague here, but we don't mind the details about this. Would be its age, would be etc. There are a lot of things that might characterize a petal. It makes a lot of parameters that must be added to the petal. If at some point I need to change my model of a petal and add another parameter, let's say z, okay, here, then I will have to change the z everywhere in my system because the module petal will appear potentially in many places of my system. So just adding one parameter would mean that as a modeler, I would need to add this parameter everywhere in my program and change and modify my program everywhere. And if I was wrong, I need to remove the z everywhere in my program. So it's very tedious and very error prone. Okay, and we don't want to deal with this. So one way to escape from this is to remove all this list of arguments from the petal definition, from the petal module, and say that a module petal as an object, petal as an argument, a petal model like this. And the object petal model encapsulates all these components. So this will be a class, because in Python an object is formally a class. So this will be a class with a length, with a width, with an age, etc. With as many things, and potentially also with functions, with methods to be associated with the class. So it's a design pattern. If you start to have modules with big number of arguments, you just stop doing all this. You put all these arguments as a class. And then you have a better modularity in your system. So this is the reason why now we have, and you're right, we are now at the next level of complexity, and we need to have this type of approach. So this is the first thing. Other questions? So this explains that we have the so I have created the sepal model, the petal model, the carpel model, the pedicel model, and that's it. And all will come with an initialization that will correspond to their key parameter, the key growth parameter, their key length, width, geometric parameters. Okay. No, I still keep, exactly as in this case, I still keep in my L system the petal modules that will take the petal models, the object petal model, as an argument. So now,
Just one question. like the condition for producing SEPA is T to be smaller than SEPA lifespan. Okay.
Uh-huh.
But isn't there a delay before the SEPA is produced?
Where is it? At which line?
Line 332.
332.
No, so the SEPA is produced at initial state. Okay.
Yes.
No.
Yes. Yes. So the T. So the in line 32, 332, you have the sepal, which is a function of T, that produces something that will be the sepal model. And the sepal model will only be produced if we have not reached the end of maturity of the sepal, where the sepal will be shedded. Will be shed. So no, let's look. It's a good strategy when you have a new file, a new LPy file, to go straight to the axiom and to the derivation rules, to see what is going on. So I see that the modules, they are flower, pedicel, petals, exactly all what we said, including the sepal model and petal whirl and things like this. And now, what are the production rules? You can see that they are restricted to very limited actions. What this says is that a flower at time t becomes a flower at time t plus delta t, t plus dt. And the sim bar, you can forget about this. This is the bar that is plot to show the progress of time. Okay, so the production rule just says a flower at time t becomes a flower at time t plus dt. Now, if I look in the interpretation rules, I see that what is a flower? A flower is a pedicel, a sepal whorl, a petal whorl, and a carpel. And they are all dependent on this time variable. Now I take, for instance, the sepal whorl, and I try to figure out what is the sepal whorl. It is here. And the sepal whorl is a loop with 4 steps that produces sepal at t. Okay, now I go and see what is a sepal. So what is a sepal is below, and I see that a sepal, I compute a tau that comes from a heel curve, we will see. So this tau will be some sort of time. And then I say that in the sepal model, I create a new sepal model class object. Well, it's not a class. From the class, I create the object sepal model. So now I start to create something that will be that will be able to store the values of the different variables of a sepal. Okay, and then I say if the time is sufficient is not maximal, then I produce a module sepal model with the class included, with the object included that I just constructed. And, which is very important, this time tau. So here there was a sort of magic where I transformed the time t into the time tau. And this is exactly the timeline warping that we discussed before. Okay, so, and this Hill function, how it makes this? It makes this by defining the Hill parameters, the delay, the mid time of the curve, the maximum value that is reached by the curve, etc. And you have all this, and all these values, they characterize the dynamics of development of the sepal. What? Okay. Okay, and now I have a sepal model at time tau, and not at time t. So sepal model at time tau, this is exactly, so this is almost independent of what is before. This is what describes the developmental stages of one sepal. So developmental stages of one sepal, I have the length of the sepal function of tau, I have the radius of the sepal function of tau, the angle of insertion function of tau, the width function of tau, and then I produce the geometry from these different elements. These different elements, the length, the radius, and the angle, they are computed by the sepal itself. So the length of the sepal is a function that I can call, that is a method of the object sepal. And so the sepal is the best object to compute its own length because it knows how it should grow. Okay? This is why it is sepal model and the length method applied at tau. With all this, I can create my sweep that will create the surface of the sepal. Okay? So this is the principle. Is that clear for you, or should we enter into other details, or should I repeat some details? Because once you have understood this, actually the whole program is made, because it's sepal, petal, carpel, and pedicel. Okay, and it's always the same. So actually, once you have understood this, you have understood everything. And you can play, for instance, by trying to synchronize differently the organ growth all together. So for instance, you may try to have the petal emerge more rapidly in the flower, from the sepal. Or the sepal open much more rapidly than what is done on the example.
I have a question. On line 33, you define centimeter as in arbitrary units, and it is mentioned that this is related to plangial grid units.
Yeah.
So does that impact the resolution of what you have in the end? Or?
It is just because, the grid. You can put it on the screen like this. Okay, I just clicked on this button. Then you can have the control panel. Where is the control panel? View control panel here on the side, and then you have grid here, and then you see that the unit size of the grid is 1, meaning that 1 square here is assumed to be the unit of the plangial grid. And here I say one of this unit is 0.5 centimeter. But it's, I mean, because I like when I construct this type of model and this starts to become a bit realistic, I like to keep track of the unit, because otherwise, if you develop your model unit free, let's say, and you want to add the unit in the end, it's really a mess. So it's very nice that you keep all the time in your construction of the different object. You keep you are attached to a temporal unit and to a space unit. So now, if you like to finish, we are very close to our actual final aim, which is constructing a realistic plant development LPI model that could be used in a system to train the system for machine learning operations. So by the way, we will learn on Friday, Ian will make a presentation showing how we can use these systems and to scan them, make sample of points, 3D cloud sample of points, so that we can train systems, machine learning systems that are that take as an input sample points in order to produce right segmentation of the point cloud. Okay, so Ian will present the next step, the steps in downstream of what we are doing here. Okay, so let's look at the complete model now. So in the complete model, we will have both branching system, a part of the model controlling the branching system, and a part of the model controlling the organ development. So you will find these two aspects. So we have already studied the two aspects, and now we are combining them. So let's briefly look at the model. So once again, as I said, so this is the model. Go directly to the axiom and to the production rules. So the axiom is just creating so here it's no longer an apex. I called it M, like a meristem. And I created meristem data, which is an object containing the data of a meristem, and I embed this object within a meristem module. Okay, so is it clear here what happens? So instead of putting all the age of the meristem, the time of the absolute time, and other potential the order of the meristem, instead of putting all this as different arguments, I encapsulated all the data in an object that is called meristem data, and then I will just manipulate from the module meristem. I will just manipulate this object. Okay, this is clear. And in the beginning, this object is initiated with what should be initiated for a meristem data that you can find in the class meristem data. Okay? Okay, and this creates only a number of staff, like sugar staff, plus the meristem data. So there is one meristem in the scene at the beginning. Then you see that there are rules here. There is one rule, at least. Let's see how many rules there are. I think we don't need the... Yes. So we have basically three rules. One that is meristem data. So, sorry, one which is transforming the meristem, one which is transforming the internode, one which is transforming the flower. I think the pedicel is a leftover from other things, so it should be removed. I think it should be removed. I won't do it right now. And you have a last one that is made for the leaves. So things that will change are meristem, internode, flower, forget about pedicel, leaf, and this is insertion angle, the insertion angle of the leaves. Okay, now let's look a bit more at the meristem rules. What it says is meristem, if their physiological age has reached 3, become a flower. So now I need to explain to you. You see that meristem, they have physiological age, and this we already explained before. So I assume that I'm a meristem, and I grow. In the beginning, my age will be 0. And after, my age becomes 1. And after, my age becomes 2. And finally, my age becomes 3. Okay? While I will be in state 0, I will produce leaves. While I will be in state 1, I will produce other things. In state 2, I will produce yet other things. And in state 3, I will produce flower. So where I don't remember exactly, but there is some place, hopefully, where I say what are the physiological ages here. So the meristem has a physiological state, I call it state here, which is 0 if this is vegetative, 1 if this is mixed between vegetative and inflorescence, and you will see that we need this, 2 if this is inflorescent state, and 3 if this is flower. So here, this is vegetative, meristem. Here, this is vegetative, it's a mixed. Here, this is inflorescential. And here, this is flower. Okay, and you see that it's extremely important because the meristem will produce things differently according to its progression along this axis. So at the beginning, the meristem, which is M, starts with a state equals 0. Sorry. So the meristem is M, and its state M.S equals 0. Then it continues to grow and produces sometimes leaves because it is in state 0. Then at some point there will be an event which depends on time t or which depends on something that creates that the meristem will go to 1. So I will move from here to here. And then I will start to be in vegetative inflorescent state. And then I will stop to make leaves. So there were leaves here made. I put them in green. And once I change my state, I will no longer produce leaf, I will produce other things. This is the idea of changing the state. You are not going to behave in the same way. Okay? So let's see how this works in the main rule. Okay? So what is written here is that in any case, if I am in stage 3, I become a flower. And for the rest of the time, this is the else that is here, I have a lateral production. And does this lateral production depend on the physiological age? Well, here I see that if I am below the stage 2, I will produce a leaf. But if I am above the state 2, which is, I won't produce this leaf because I skip this part. I skip this line here in which I produce the lateral leaf. So obviously, I produce leaves in these two states. But not here, there are no leaves. Which is consistent because in the vegetative state, I have leaves, and in the intermediate state, which I will show you now, okay, you see this stage where I have long internodes, I have lateral leaves. This corresponds to this vegetative inflorescent state. Vegetative means the plant is not producing flowers, so rather produces a leaf, okay? But it starts to be an inflorescence. It starts here in the VEC 0, the internode are very small. They are close to 0 in length. Here in this part, the internodes start to elongate. So what is the difference between stage 1 and stage 0? They both contain leaves, but in the stage 0, the internodes are very small, close to length 0. while in stage 1, the internodes are elongated, and this is what you see here. The internodes are elongated with a leaf. Okay. If you continue, you see that the plant is growing, but after this stage, in the efflorescence stage, there are lateral flowers, but there is no more leaf. You see here, for instance, this one, this one, this one, this one. There are no leaves here. So in this part, there is no leaf, and there is a there is a lateral flower. Okay, so actually, what you see here, it's very short portion of code, is actually expressing these rules, which are the rules for the construction of the Arabidopsis system. And what you should remember is that for this, I am using this notion of physiological age or physiological state. I assume that the meristem goes through a list of states, and in each state, so he's able to make the transition. We didn't see what is the event here. What makes the transition? So we can have a look at this. But upon this transition, I will move to a different state and then be able to produce different things. Lateral leaf or not lateral leaf. Okay? So what about the transition? Here, there is apical transition, and here there would be lateral production. These are two functions, and these two functions are defined above. Okay, so in the lateral production, I will decide what is the. No, sorry, it's not lateral production. I want to speak about the. Where is the function? Apical transition, yes. I want to speak about the apical transition. So the function that will take care about the event. What is the event that will make possible to switch on the main stem of state of the meristem? So this is described in this apical transition, and for instance, here we say that if I am in a state 0, I am at the very beginning of growth, so I'm producing leaves, and the number of the state, the duration in which I was greater than a certain amount, so the number of leaves was greater than a certain amount, then I will pass to a vegetative state. So here, basically, it says that after a certain period of time, we don't want to model this too precisely. After a certain amount of time, the meristem goes automatically from stage 0 to stage 1. Okay, and you have different types of conditions that will make the transition from stage I to stage I plus 1. Okay. Okay. And then there is a similar function to compute the state of the lateral meristems, which might be different from the stage of the apical meristem, and this is handled in this lateral production function. And you see a bit the similar type of pattern. Well, depending on some conditions, you will compute a specific state of your lateral meristem. And each meristem, once I know its state, I'm able to compute its production. I know how it will work. Is that sufficiently clear? Okay. And the rest? So now we know how the meristems are going to change. And depending on how they change, they will produce organs. And you know now that how the organs are being created. you see that the meristem, when it is producing a flower of tea, well, the flower of tea, you know how it will be handled. This was the previous file. Okay. Okay. I think this is more or less all what you need to know at a macroscopic level. Would you like to finish and have a look to the file to see whether you managed to recognize a bit the elements and maybe see whether you have questions, and then we can end on this.